All right, for our first example, I want to look at this case of the rock being swung around in a vertical circle. So I'm going to redraw this and change our view a little bit so that we can see what's going on. So here is the rock that is being swung around along a circular path. There's its path, and the rock is right here at some point. It's moving sideways with a velocity v, and there's a string attached to it from the very center of the circle. So as time goes by, this rock is going to go up and around and swing around this way. This string has some length that makes the rock travel in a path of radius r. And what I want to do here is solve for the tension T in the string. So I want to find how much tension there must be in the string to make this rock go around in a circular path. We'll solve this problem like we solve any problem involving Newton's second law. We'll draw a sketch, which I've done here. We'll draw a free body diagram, and we'll write out Newton's second law. Sum of the forces equals ma. Let's do the free body diagram of the object right here at the bottom of its path. So free body diagram of the rock here. We have the weight going down, mg, and as we saw in the last one, we have the tension going up. That's what the free body diagram looks like. There are two forces acting on this rock. Weight going down, tension going up. If I add them together, they're going to give me ma, the mass times the centripetal acceleration. So these two forces, T minus mg, would be considered the centripetal force in this case. Let's add up all of the forces in the vertical direction, and we'll set that equal to ma in the vertical direction. This is our positive y direction, so that when I add these, I get positive tension minus the weight equals m times a. Now the a in the vertical direction is the object's acceleration this way. That's the acceleration toward the center of the circle, and that has magnitude v squared over r. So when I come to this a, I'm going to replace it with v squared over r. So I get m v squared over r. And I can solve for the tension. How much tension is in the string? If I move this mg term over here, I can factor out a mass and see that the tension is v squared over r plus g. And it tells me that the faster I move this rock, if I spin this rock around faster and faster and faster for a given radius, then the tension increases. And you can totally feel this if you go outside, have something tied to the end of a string, and spin it around in a circle. The faster you make it spin, the harder you have to pull on your end of the string to make the thing move in a circular path. So as V increases, the tension increases. It also goes up as the mass. If you tie a heavier object on the end of the string, the tension goes up. You have to pull harder to make it go in a circular path. Now this one's interesting. It also goes as 1 over the radius. This is another thing you can try. You have to pull harder as the circle gets smaller. So try this with something. Spin it in a small circle at some speed, and notice how hard you have to pull on the string. If you make the circle bigger, then you will find that for the same speed and mass, you don't have to pull on the string as hard. As the radius gets bigger, the tension in the string goes down. Okay, let's take another look at this problem. Instead of finding the tension at the bottom of the motion, let's let the rock go up here so that it's at the top, moving this way at the same speed, and let's find the tension there. So there's the string now. Okay, so we're going to redo this, just moving the rock to the top of the motion. Let me erase this free body diagram, and I'm going to erase the sum of our, well, you know what, let me leave that bit so that we can compare as we go. Let's redraw the free body diagram. At the top of the motion, there are still two forces acting on the rock, but now they're both directed straight down. The tension is pulling the rock down, and the weight is always going down. So the free body diagram now looks like this. Here's the tension, the string, pulling the rock down, and the weight, mg, is also going down. So what happens when I sum my forces? I have tension going down and weight going down, minus T minus mg. There's one other change we have to make. You have to watch out for this one. It's an easy one to miss. The acceleration is toward the center of the circle. The acceleration is down this way now. If I was to draw it in orange, the acceleration would look like this. It's down. So v squared over r is also in the down or negative direction. So we pick up a couple negative signs here. And if I solve this for the tension T, what I find, after factoring out the mass m again, is that now the tension is m, v squared over r minus g. So at the top of the motion, the tension is still increasing as we spin it faster and faster, and it's still decreasing as the radius gets bigger, but notice that it's now v squared over r minus g. So I can imagine if I'm spinning this thing at some certain speed and there's tension in this string so that I'm pulling on it to make this rock go in a circular path. If I slow the spin down and I slow the spin down farther and keep slowing it down, the tension is going to decrease, and at some point the string becomes slack. There's no tension in this string, and at that point the rock no longer moves in the circular path. It's just going to fall along a parabolic path because gravity is the only force acting on it, and it's in free fall. So I can reduce the speed down until the tension equals 0 when the rock is moving at the minimum speed required to move in a circular path. And the question is, how fast does the rock have to go to move in a circular path so that the tension doesn't go to 0? We can find that by saying the tension is going to equal 0 when this thing here equals 0. And if you solve this for v, you find that v min equals the square root of g times r. So the slowest speed that the rock can have before the tension drops to 0 is square root of g over r. The larger the radius, the faster you have to spin the rock. And you can see this when you're trying to get a rock started, spinning it in a circle. It's easier to start that motion if the circle is small, because you don't have to spin the rock very fast. If r is small, v is small, and it's easy to get the rock going. But if you try to get the rock going in this circular path for a large circle, you have to have a very high speed, and it's hard to get it going. So the way you normally do this is to start it with a small circle, where v min is small, and it's easy to make it go in a circular path, and then you can let some string out and let it go into a larger circle. All right. So there's one example. There are several other problems that I'll link after this, so you can have a look at those.